All right, hello class. This lesson is on solubility equilibrium, and it pairs well with your solubility equilibrium FRQs. There are 3 total play posits in this sequence. By watching this one, we'll be able to write the expression for the solubility product constant for a salt. We'll be able to calculate something called KSP from solubility data, and we'll be able to calculate solubility from the value for KSP with 80% accuracy. We're also going to be able to calculate the effect of an added common ion on the solubility of a slightly soluble salt. So if you think back to honors or even at the beginning of the year, we know that there are solubility rules that exist that allow us to qualitatively determine whether or not something is soluble or not. In AP, now that we have knowledge of equilibrium, we can actually do some math to figure out to what extent it will be soluble, and we'll be able to figure out concentrations from that. So experimentally, we can consider solubility equilibria to make predictions about the amount of a given salt that will dissolve. So KSP. KSP is the equilibrium constant for the solubility product. That's what SP stands for, solubility product. And that is the equilibrium for the solid and its ions in a saturated solution. So something that we're going to really have to pay attention to is net ionic equations. If you are lost at any point in time in this play posit, please go back and review net ionic equations, because that may be where we may be struggling. The nice thing about KSP is that it's a measure of how much solid dissolves to form a saturated solution. If we think about this in terms of equilibria, I've got an example. If we want to write the solubility product expression for CaF2 dissolving, we can look at it this way. First, let's write a balanced equation. Include your states of matter. All right, so we've got, there you go. We need to pay attention to charges here. This would split up into its ions in solution, assuming it dissolves. And then we'd have 2 F-, and those are both aqueous. Okay, so if we consider how we would normally write an equilibrium expression would be written with only the gases or aqueous components of the reaction. We don't ever write the solids in there, and we don't ever write pure substances. So the nice thing is CaF2 would not be in our KSP expression. So we can just say KSP is equal to my calcium ion concentration times my fluoride ion concentration. And remember that we have to respect the stoichiometry, so that would be squared due to the balance equation. Okay? So take a moment and tell me what the KSP expressions would be for the next 2 compounds. You may have to review some of your charges. Phosphate is a 3- charge, and sulfate is a 2- charge. Good luck. Okay, so the first one, we could look at our solid here, and we know that that would split up. I'm sorry, I forgot my states of matter. Oop. We know that would split up into 3 magnesium 2+, and that is aqueous, and 2 phosphate ions. It's a good time to review those polyatomic charges. They're going to be super useful for the rest of this unit. So then our KSP is going to be, Mg2+ cubed times phosphate ion 2- squared. Okay. We can break down barium sulfate in a similar fashion. We have our solid, we've got barium 2+, that's aqueous, And we end up getting KSP equal to barium 2+, and my sulfate 2-, just like that. Pretty easy. Okay, so now on to the actual math. So, what can we use this for? Well, if we are able to measure the solubility in the lab, we can take that concentration and determine our KSP. So this one, copper 1 bromide, has a measured solubility of 2.0 times 10 to the negative 4th molar. Calculate KSP. All right, first things first, I always give myself the net ionic equation. Sometimes they'll give you other components in the question. Usually we know that double replacement reactions result in new precipitates, but we know there are always spectator ions. In terms of the KSP, we only care about what's participating in the precipitation reaction. We don't care about things that are spectators. So this one is nice, they only gave us one thing, so it's pretty easy. You just look at copper. If copper is a 1+ charge and bromine's a 1- charge, it's just a solid CuBr. And we know that's going to split up into Cu+, aqueous, and Br- aqueous. Okay? So that means that our KSP is going to be Cu+ concentration times Br- concentration. Well, the nice thing about this is that we have that molar solubility concentration already, and we can plug that straight in. So, here we go. We've got KSP equal to 2.0 times 10 to the negative 4th molar for copper plus, and the same concentration for Br-, because it's a 1-to-1 ratio. So on my calculator, 2.0 e to the -4 times 2.0 e to the -4. Could have saved yourself some time just by squaring it, but we get 4.0 times 10 to the negative 8th. This is our KSP value. Okay, this time for number 2, I want you to try it on your own for bismuth sulfide, and it dissolves with a molar solubility of 1.0 times 10 to the negative 15th. So find KSP. Okay, we need to know the charges that this will dissociate into. So we've got bismuth, which is a 3+, sulfur, which is a 2- charge. So I set up my equilibrium just like I did before. And I wrote that x is equal to 1.0 times 10 to the negative 15th. That is my molar solubility. I'll talk about what x means in the next problem. But for the purpose of what we're doing, we just plug that back into our expression. And bismuth would be squared, sulfur would be cubed. So all in all, we end up getting 1.0 times 10 to the negative 75th, which is our KSP, which is really, 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 really small. So not that much of this, you can tell just by the small number, not that much of this actually dissolves very well. Okay, on to the next one. So this is the third example. All three of these examples so far have been in the NAMESY packet. This is the third example. It says the KSP value for copper 2 iodate is 1.4 times 10 to the negative 7th at 25 degrees. Calculate its solubility. Whenever we're told to calculate solubility, we're talking about molar solubility, aka just a concentration. So let's look at our equilibrium expression. And we know this is our solid. And we're going to end up, we're told copper 2+, which is nice. Some of the problems are mean to you and make you review the naming rules, so we'll just keep an eye out for that. Iodate's a 1- aqueous, okay. And this means that our KSP expression is going to be Cu2+ times, oh, I'm sorry, I forgot to balance, 2 iodate, which means iodate concentration squared. And this is going to be equal to 1.4 times 10 to the negative 7th. So how in the world are we going to solve for our concentrations here? Well, in a sense, we're going to treat this like a rice table because it's still equilibrium. So what we really need to know is our change in that C column, right, of the rice table. So we know that the change is going to be proportional to our balance equation. So copper 2+ has a change of X, and iodate has a change of 2X. So what we can do is we can take that change and we can plug that back into our KSP expression. So we've got X for copper 2+ and 2X squared for iodate. And this is going to be equal to 1.4 times 10 to the negative 7th. So let's consolidate a little bit. 2x squared would give us 4x squared, times x would give us 4x cubed. So we know 4x cubed is equal to 1.4 times 10 to the negative 7th. And I can go through 1.4 times 10 raised to the negative 7th. Divided by 4. And that means 3.5 times 10 to the negative 8th is equal to x squared. You betcha. We got a cubed root in here. So to solve for x, we need to do a cubed root. Now, real quick, there's two ways you can do this. If it's a cubed root, if you go to math and then number 4, they actually have that cube root button for you, which is great. We're going to get our x value equal to, I'm going to put this in scientific notation, 3.3 times 10 to the negative 3 molar is my solubility here. Okay, so the cube root button is great. The other way you can do it is you can put in the cube that you want. So let's say 3, and go to the math button, and then go to number 5, where it has x and then the square root. And then we can put in the number we want. So 3.5 e to the negative 8. Okay. Enter, and it gives us the exact same answer. So sometimes we're going to have some roots that are a lot larger than the cubed root or the square root, and that's how you do that. Plug it in that way. Okay. So iron 3 hydroxide. What is the molar solubility for iron 3 hydroxide? Now I will give you the KSP that I used before you start solving. The one I had, and it may differ from your table, I had a KSP equal to 1.8 times 10 to the negative 15th. So use that to solve your problem. Good luck. Okay. So here we are. Iron 3+ means that we've got an Fe3+. We have 3 hydroxide here, so the balancing is important. 1.8 times 10 to the negative 15th is my KSP. So I just took that change, plugged it back into my KSP expression. So x times 3x cubed. Well, first 3 cubed is going to be 27. So 27x cubed times x gives me 27x to the 4th. And then I got 1.8 times 10 to the negative 15th. So again, I might have to do that special thing before. So I put in the number, go to number 5 under math, 4 with the cubed root, or the 4th root. So after I went through and did my division, I got 6.66 e to the negative 17. Okay. And I get 9.0337. I guess went before when it was 6.6 repeating, I rounded up to 9.04, but it's close enough. 10 to the negative 5th molar. Okay. All right. Now the last one. This one's tricky. This says, what is the molar solubility of calcium fluoride in a 0.010 molar sodium fluoride solution? And they give me my KSP. So first, let me talk about this one for a little bit. I will have a more formal slide on this in a later play posit. But first, we have to recognize that this is a common ion problem. We've got fluoride. What happens is calcium fluoride, they said they're trying to dissolve it in sodium fluoride. So we're using a different solvent. Now, with that different solvent, that means we have extra fluorine ions already floating around in solution, which can impact our equilibrium. So the presence of a common ion will cause the equilibrium to shift so that even less of the substance with the smaller KSP value will dissolve. So if we think about it this way, we've already got a lot of stuff in our solution. What happens when you put too much stuff in your solution? Well, not enough of it will dissolve. It will stay as a precipitate, right? We get saturated, or to a certain point, even supersaturated. I'll talk about later that we also know that pH can affect our solubility, and it's related to the same idea because that H plus or OH minus ion can affect the shift of our equilibrium, especially if we have ions that will react with them. So in this particular one, we need to look at our NaF, and we still need to look at our regular KSP. So we know that we have calcium fluoride, and we get Ca2+, which is aqueous, and 2F minus, also aqueous. Okay? So set it up just like any other problem. We know KSP is going to be equal to calcium and our fluoride squared. And we know that this KSP is 3.9 times 10 to the negative 11th. Okay. So, what's tricky about this problem? Hold on, let me find my notes here. Okay. So what's tricky about this problem is that normally we're dissolving things in water, right? So the only source of fluorine is our solid that is dissolving. Here we already have fluorine in solution, so we need to account for that when we're trying to figure out our molar solubility. So before, when we're looking at our change, we could say our change is x and 2x. Well, we actually can ignore this part because this concentration here is very large in comparison. We know that whatever our molar solubility is going to be, it's going to be small because our KSP is 3.9 times 10 to the negative 11th. So we can ignore the 2x here. And what we can really do is plug in, why won't my pen work? What we can really do is plug in the concentration we are given for F. So 0.010 molar F minus, and that is equal to 3.9 times 10 to the negative 11th. Okay? Now remember, it's 0.01. This is messy. Let me rewrite this with my pen working this time. So we can plug this in. So 0.010 molar F minus. And remember, that is squared. And this is equal to my 3.9 times 10 to the negative 11th. Okay, so if I want to solve for molar solubility, anytime I say molar solubility, and I'm referring to x. So I want to solve for x. Here's my x. So 3.9 times 10 to the negative 11th divided by 0.010 squared will give me my x, which is my calcium concentration. All right. So let's do that in the calculator. 3.9 e to the negative 11th divided by 0.01 squared, and I get 3.9 times 10 to the negative 7th molar. Okay. And that is my answer. Now on the on the Namesy video, I believe Renee McCormick used a different concentration. So if you watch that also, yes, my numbers are going to be a little different. I think she used 0.025 NaF instead. Now, if we were doing this the regular old way, without anything, if we're doing this in water instead, so this is an NaF, right? As our solvent. We can compare this to if it was in water and see the difference and why we have to do it this way. The effect of a common ion, if you will. So we already said that x and 2x were my equilibria, had this been normal. So 2x squared gives us 4x squared. 4x squared times x gives us 4x cubed. So what we're really looking at, we could have been looking at 3.9 times 10 to the negative 11th divided by 4, and then we could have done the cubed root. Or why I want to give me the cubed root. Okay, cube root of this answer, here we go. And we would end up getting molar solubility of 2.1 times 10 to the negative 4th. Okay, 10 to the negative 4th molar, and this is in water. Okay, so I just solved it like normal, like the previous examples. But the key here is that we want to look at these two numbers. Which one's larger? Well, water's larger, which means we can dissolve more stuff in water. If we have common ions already in our solution, we can't dissolve as much. And it shows here. We can only dissolve a small amount of the calcium fluoride. Since we can only dissolve a small amount of calcium fluoride, we end up with more solid, and things stay as a precipitate. So there is a reason for looking at the common ion effect. Before we could, think about it qualitatively, but now we have a way to justify it with numbers. Okay, have a great day.